This paper addresses a common problem in robot grasping using deformable gripper jaws. False negatives due to overly conservative planar surface contact models. We propose a more realistic non-planar surface contact model based on a 6D limit surface. Let's look at an example. Humans are able to grasp a cup and hold it like this. The grasp is able to counterbalance the object gravity. If we use a planar contact model to analyze the grasp, the frictional force will not be able to resist the gravity because it has to lie in the plane. Therefore, we need a non-planar surface contact model to analyze such grasps. Deformable gripper jaws or compliant tactile sensors are widely used in robot grasping as they deform to the local geometry of the object and increase grasp robustness. Grasping with these jaws results in non-planar surface contacts if the local geometry of the object is non-planar. For such contacts, the frictional force and torque are both in 3 dimensions, and their combination, which is defined as the frictional wrench, is 6-dimensional. In this paper, we model the 6D limit surface, which describes all possible 6D frictional wrenches that can be transmitted through a non-planar deformable contact. The proposed concept of the 6D LS is generalized from the 3D limit surface, which models the 3D frictional wrench limit for planar surface contacts. Existing work in grasp planning typically assumes a planar contact area and uses an ellipsoid or aquatic function to approximate the 3D limit surface for computational efficiency. Applying such planar contact model to non-planar deformable contacts leads to over-conservative friction estimation, as the model do not consider the non-planar surface geometry and only computes a 3D subset of the 6D frictional wrench. In our previous work, as shown on the left, we considered the non-planar surface geometry but only computed a 3-dimensional subset of the 6D frictional wrench. Related work on the right modeled the frictional wrench for non-planar surfaces by discretizing the contact surface to planar elements and fit a 3D LS model for each element, which is less efficient for fine surface geometry. While existing work either assumes a planar contact surface or decomposes the surface into planar elements, we model the 6D frictional wrenches for a non-planar deformable contact with a single limit surface. Given a contact surface and a pressure distribution, we model a 6D limit surface that bounds the set of all possible 6D frictional wrenches that a deformable gripper jaw can exert on the object. To compute the limit surface, we assume column friction and a known contact profile. We then apply the 6D LS models to predict physical grasp success by building a grasp wrench space. We assume that the change of the contact profile is minor during the manipulation, and we also assume quasi-static physics, which means the inertial terms are neglected. We now introduce the computation for the contact wrench, which consists of the wrench impressed by the pressure defined as the normal wrench and the frictional wrench. The illustrated gray surface is a representative non-planar contact surface between a rigid cup and a deformable gripper jaw. Given the contact surface and the pressure distribution, the local normal force at a point is antiparallel to the surface normal at this point. The normal wrench with respect to the pressure center O is computed by integrating the local normal forces and torques. While the normal wrench only depends on the contact profile, the frictional wrench also depends on the relative motion between the grasped object and the gripper jaw. We start with formulating the instantaneous object motion, defined as twist. A twist is a combination of a translation along an axis and a rotation about the same axis. The axis is defined as the instantaneous root axis, short ISA. We model the ISA as a line L with direction E and goes through the point Q. The linear velocity at a point consists of a velocity parallel to the ISA and a velocity perpendicular to the ISA. The sum is the linear velocity of the object at this point. A twist at a point consists of linear and angular velocity. As the magnitude of the angular velocity does not affect the frictional wrench, we define a unit twist, which is a twist such that either the magnitude of the angular velocity is 1 if the motion includes a rotation, or the magnitude of the linear velocity is 1 for pure translations. Given a unit twist of the grasped object, we derive the local frictional force at a point. On the right, we see an enlarged view of the contact surface and a representative point on the surface. We also see the surface normal and the tangent plane at this point. Given a scalar pitch and an ISA illustrated as the line L, we first compute the linear velocity at this point, which is the sum of the velocity parallel to and perpendicular to the ISA. Next, we compute the direction vector of the relative velocity by projecting v onto the tangent plane. The local frictional force is antiparallel to the relative velocity. Here we see two representative object motions and the corresponding local frictional forces illustrated as green arrows. In the first example, the cup rotates around the negative y-axis relative to the gripper, and we see the local frictional forces that resist this motion. In the second example, the cup is a pure translation along the gravity direction. Given a unit twist of the object, we obtain the 60 frictional range for the whole nonplanar surface contact by integrating the local frictional forces and torques. For the two object motions, we obtain two corresponding frictional ranges illustrated as orange dots on the right, which is a 3D projection of the 60 frictional range space. A 6D limit surface can then be obtained by sampling each of the possible motions and compute the corresponding frictional range. Here shows a 3D projection of the 6D limit surface by densely sampled the motion space. We also plot 2D projections to get an idea what the limit surface looks like. We know that densely sampled motion space and compute the frictional ranges is potentially time-consuming. Therefore, we compute a finite set of the frictional ranges by sampling the unit twists and fit the model to the ranges. The figure on the right shows the normalized frictional ranges where each component is between -1 and 1 for numerical stability. We fit two models to the normalized frictional ranges, a 6D ellipsoid and a fourth-order polynomial, referred to as the quatic model here. For an ideal limit surface model, the frictional ranges should be on the surface. Therefore, the objective here is to minimize the distance of frictional ranges to the surface. The functions f1 and f2 define an ellipsoid and a quatic respectively. The last part is the convex constraints for the two models. To evaluate the LS models, we define the range fitting error, which is the mean distance of the range samples to the limit surface. We now introduce the algorithm to predict physical grasp success by building a grasp range space with the proposed 6D limit surface models. We show the pipeline for a parallel jaw gripper, but the algorithm can be applied to grippers with any number of jaws. For each contact, we first compute a finite set of the frictional ranges by sampling the unit twists. We then fit a 6D LS model to the normalized frictional ranges, followed by linearizing the LS models. By combining the frictional and normal range, we have the contact range constraints for each jaw in a local contact frame. We then denormalize them and transform them to the object frame. By computing the Minkowski sum of the two sets of constraints, we obtain the grasp range space, which is the total force and torque that the grasp can act on the object. In the physical experiments, we compare the GWS constructed with the ranges from the initial sampling and with the evenly distributed linearized limit surface models. We start the evaluation of the two proposed 6D LS models with nonplanar parametric surfaces as contact profiles. We further evaluate the models with more than 2,900 contact profiles obtained from the FEM simulations. For both parametric and discrete surfaces, we observe that the quatic model has a lower fitting error than the ellipsoid. Here's a representative 3D cross-section of the quatic and the ellipsoidal 6D LS model. The range samples are closer to the quatic surface compared to the ellipsoid, where large differences can be observed within the rectangles. We also applied the proposed 6D LS models to predict physical grasp success for a vertical lifting task. We 3D printed 10 rigid objects of two types, which are grasped by the deformable gripper jaws with a fin ray structure. A wrench disturbance assembly is attached to the object to control the external disturbances by mounting the weight plates at various locations. We compute the predictions with 7 baseline contact models for more than 1,000 physical grasps. Results in the table show that the proposed 6D-LS models reduce false negatives by up to 26% with similar precision. We now discuss the limitations of this work with future work marked in green. The power law pressure distribution is based on the assumption that the pressure is symmetric about the object center, but the FEM simulation results on the right show that this may not be true. Furthermore, the contact profile can change during the manipulation. One way to address these two limitations is to measure the contact profile by using a deformable tactile sensor and constantly update the profile and the limit surface during the manipulation. Furthermore, the contact surfaces evaluated in the physical experiments are restricted in elliptic cylinders due to the design of the fin ray jaws. We intend to evaluate more complex contact profiles in future work with examples showing on the right. We expect a larger difference between the planar and the non-planar surface contacts for such grasps. We also plan to increase the computational efficiency by applying deep learning so the fitting process can be completed at millisecond level. A neural network can be trained to output a 6D-LS model given a tactile sensor image or an estimated contact profile. This paper addresses a common problem in robot grasping using deformable gripper jaws, false negatives due to overly conservative planar surface contact models. We propose a more realistic non-planar surface contact model based on two 6D-LS models. More details can be found in the paper. Thank you for watching this video.